Welcome to the video for Lecture 24, Section 1. This video introduces you to some new MATLAB commands that will make it easier to plot the time-dependent responses of the overall transfer functions of various closed-loop process control systems. The purpose of all this process control work is to be able to estimate how a system will respond to different process inputs and process settings. As the overall transfer functions become more complex, we produce higher-order equations and dynamic responses, and we want to use MATLAB to plot those results so that we can see how well the system performs. In the previous video on second-order systems, we talked about several transient response characteristics that people use to assess the dynamic response of a closed-loop control system that may have only feedback control or might also include either cascade or feed-forward control too. Good control in Section 26 of the course packet will be defined as control in which the maximum overshoot is 25% or less and the decay ratio is about 0.25 or 1/4. You may in certain circumstances have other performance criteria. We will use the water heater problem to illustrate the procedures and MATLAB commands needed to plot the time-dependent response to a step change for the servo problem when we have a set point change in TR and the regulator problem when the inlet temperature TI changes. We will use different control modes including proportional control only, proportional plus integral, and proportional plus integral plus derivative control. I will also change the feedback element response. Here is a block diagram with the respective element transfer functions. The first step, which we have done many times before, is to write the servo problem transfer function for the fluid heater, T over TR. Values for G, H, and kV are given at the bottom of the slide. We have assumed that the gain for the actuator kV equals 1. For this first example, let's assume that the sensor and the feedback element are very fast relative to the fluid heating system, so that we can assume that the sensor and feedback element have a time constant equal to 0. This means that the steady-state gain of the sensor and feedback element is equal to 1. Finally, we will assume that the gain of the proportional control controller, Kp, equals 82.73. This value is 2 times the product of rho times V dot times C sub P. Given that the fluid heating tank is 1.2 cubic meters and the steady-state flow rate is equal to 0.01 cubic meters per second, the fluid heater time constant tau p is 120 seconds. If we substitute the values into the transfer function and simplify the equation by multiplying the numerator and the denominator by 120 times s plus 1, the transfer function simplifies down to 2 over 120 times s plus 3. This is the servo problem transfer function for the fluid heater problem. Here is the fluid heater transfer function for the regulator problem when the inlet fluid temperature Ti can change. Making the same assumptions, we can find the simplified regulator transfer function after we substitute in the appropriate numbers. So the regulator problem transfer function T over Ti is 1 over 120 times s plus 3. Here are the two equations with the numbers. Please note that the denominators are the same. Now that we have our transfer functions, let me introduce the MATLAB commands we will use to fill the array with the time-dependent temperatures of the fluid heater output. The first command to introduce is the transfer function command TF. The transfer function command is used to define a transfer function using the numerator and denominator coefficients. At the bottom is the transfer function for the servo problem, and next to it is the MATLAB command that defines the variable G3 as the transfer function given by 2 over 120 times s plus 3. The second command that we will use is the step change command. This command calculates the transient response to a unit step change for the transfer function given by the variable f and the time steps in the time function array t, which we have not talked about yet. This slide shows a couple of ways to create the time step arrays. For both examples, the time step array name is t. In the first example, the time step array t is defined by the start time, which for process control problems is usually time t equals 0, and by the stop time, which is given by the number, say, 300 seconds, and the specified increment time between steps, which we can say is 10 seconds. This command will create an array starting at 0 and going to 300 that will have values of 0, 10, 20, 30, and on until 300. Another way to fill a time array is to use the command linspace. Again, we need to specify the start time and the stop time, but this time we can give the number of points that we want in the file. To create the same time file as the other example, we need to make points equal to 31. Both methods work. Pick the one that you prefer. Here are some MATLAB commands for a script that creates the time array, defines the servo problem transfer function, defines the regulator problem transfer function, and creates the servo and regulator problem responses to unit step changes. The results are in array Y1 and Y2. These are the two arrays that we will want to plot with a T array that gives us the time steps. Here are the MATLAB commands to plot the servo and regulator problem responses. You may want to review the material in Appendix A and what you did in Lab 4 to help remember what all the commands do. Before I show the results, let's review what we have done. We have written the transfer functions for the regulator and servo problems for the fluid heating system using proportional control, and we have had the system experience a unit step change in the set point and in the inlet water temperature. Here is a plot of the two results arrays Y1 and Y2. The top line is the servo problem results, and the lower line is the regulator problem results. For the servo problem, we have changed the set point from 0 to 1. So ideally, the process output temperature should equal 1. But it does not because of the offset that proportional control produces when it experiences a step change in one of the inputs. The offset is 0.33 degrees Celsius. This is the difference between the output temperature 0.67 degrees Celsius and the desired 1 degree Celsius output. For the regulator problem, the cold water temperature increased by 1 degree. Ideally, the controller would produce water with 0 degrees output. Again, we have an offset, and the amount is 0.33 degrees Celsius. This is the difference between the output temperature 0.33 Celsius and the desired 0 degrees Celsius output. We have talked about this before. When proportional control is used alone, it will produce an offset if the error is constant. Step change inputs create constant errors. Proportional control is commonly used by itself in the inner loop when adding cascade control to a feedback system. We can eliminate the offset by using proportional plus integral control. In the block diagram, it is a simple matter of changing the transfer function in the controller element. So if we keep the previous assumptions that tau m equals 0, so that the sensor and feedback element transfer function h equals 1, that the gain of the actuator kV equals 1, and that the proportional gain Kp equals 82.76, and that tau p equals 120 seconds, and assume that tau I is 5 seconds, we can substitute the values into the new servo problem transfer function shown in the lower right corner. And after substituting the values, we set the servo problem transfer function T over Tr equal to 10 times s plus 2 over 600 times s squared plus 15s plus 2. Now if we look at the expression, we can see that we have a second order transfer function, and we can get some indication about how the transfer function will respond by finding out what the delta value is. If we know what delta is, we can see if the process is underdamped, critically damped, or overdamped. But before we can do that, we need to make sure that the last term in the denominator is a 1. We can make the 2 a 1 by dividing through by 2. After we divide the numerator and denominator terms by 2, we get that the transfer function is 5 times s plus 1 over 300 times s squared plus 7.5 times s plus 1. We can find that tau is equal to the square root of 300, which equals 17.3. Now that we have tau, we can find delta by setting 7.5 equal to 2 times delta times tau. And we find that delta is equal to 0.22. This means that the servo response with PI control will be underdamped. The value is actually below the recommended delta values from 0.4 to 0.8. We can do the same with the regulator problem, and we get the regulator problem transfer function using PI control is 5 times s over 600 times s squared plus 15 times s plus 2. You will notice that the denominator is the same. This means that the delta value for the second order response is again 0.22. Here are the MATLAB commands for finding the servo problem time response y1 and the regulator response y2. The data will be plotted every 10 seconds from 0 seconds to 600 seconds. Here are the plotting commands. Again, you are encouraged to look at the material in section 23 and Appendix A. This slide shows a graph of the two time domain responses. The top line with the circles is the servo problem, where the set point was changed from 0 to 1. As expected, the response is underdamped. The maximum overshoot is about 0.5 degrees Celsius. We probably are within about 5% of the final response by around 250 seconds. The lower line shows the regulator response when the inlet water temperature increased by 1 degree Celsius. The set point did not change, so the desired temperature is still 0 degrees Celsius, and the response, as expected, based on the value for delta, is underdamped. These results were found assuming that the integral time tau I was set to 5 seconds. If we change the integral time tau I to 10 seconds, the new servo and regulator problem transfer functions become the equations shown. The new second order denominator is 1200 times s squared plus 300 times s plus 2. To calculate delta and see how the transfer function responds, we need to divide through by 2 again to make the last term in the denominator a 1. Then we can find the values for tau and delta. They are tau is equal to the square root of 600, or 24.5, and delta is equal to 0.306. Here are graphs for both the servo and regulator problems. The colored lines without markers are when the integral time was set at 10 seconds. The servo problem response has a lot less overshoot, and the output is within 5% by 150 seconds. The regulator response has about the same overshoot, but oscillates fewer times when the integral time is changed from 5 to 10 seconds. For all of the previous examples, we assume that the sensor and feedback element had a constant gain of h equal to 1 because we had set tau m equal to 0. Now let's assume that the sensor and the feedback element have a first order response and that tau m is equal to 50 seconds. Here is the servo problem transfer function using proportional control only, and the first order transfer function for the sensor and feedback element with tau m equal to 50 seconds. After putting in all the numbers from before, the transfer function becomes 100 times s plus 2 over 6,000 times s squared plus 170 times s plus 3. We divide by 3 to make the last term in the denominator a 1, and we can find that delta for this situation is equal to 0.634. Here is the regulator problem transfer function. The result after substituting in the known values is 50 times s plus 1 over 6,000 times s squared plus 170 times s plus 3. Since the denominator is the same, the value of delta is the same. The time-dependent servo and regulator water heater outlet temperature responses using proportional control are shown here. Both have some overshoot, which was not seen in the previous case when tau m was equal to 0, and we use proportional control. We still have an offset with proportional control alone. So now if we use proportional plus integral plus derivative control, or PID control for short, we get the two transfer functions shown. The numerator of the servo case now has a second order term. The value for delta is equal to 0.2. More details are presented in the course packet. Here is a plot of the servo and regulator responses using PID control. These are not well-tuned controllers, but they show the underdamped responses we would expect. Again, more details are presented in the course packet. This brings me to the end of the Lecture 24 Section 1 video. Write down any questions you have and bring them up in class.